Okay, so after conducting a sensitivity analysis, the next step is to perform calibration. Yeah, for manual calibration, you can go through all of them and see how each one is doing. You can also you can always check your indices here. Now, the routine here is simple. You first of all enter your parameter value. Let's say you want to try 17, let's say. Then you run with the current parameter set, run, and then it goes. And then once it has finished running, you click on refresh model performance. This will refresh the indices as well as the graphs, so you can now go back to the graphs and see. It seems like your model is overestimating flows quite a lot. You can see that by the p bias, but also the NSE. It doesn't look so good. Okay, you know, it's maximized. Uh, doesn't look so good. All right, so maybe that's the wrong direction. Maybe we should reduce the curve number to -2. And again, I'm doing this based on the parameter lists, I mean the sensitivity indices here, starting with the most sensitive one, and then you go down there. So, okay, I'm just going to sort this using the name so that every time I know that it's always on the second position. I change it to number 2 and run. So if you want to change, you double click to make it editable. So I run again. And once finished, again, I do refresh, watch the numbers. So it seems like we're going in the right direction if we are reducing the curve number. And you do this again and again. If you want, by the way, to refresh, you don't have to go to something else and then back. If you want to see, you can just double click. If you're already there, you just double click and then it will change the graph. I will demonstrate it by running it with 7. First of all, refresh performance and then double click. Okay, yeah. So now if you double click, then it will update the figure. That's pretty much the manual calibration. You change the parameter, run, refresh performance, check the indices, check the graphs. Are you happy? No. Then you change again. And the cycle goes and again and again. It's the same manual calibration you do, just that the toolbox is helping you in making the process easier and simpler. And by the way, check out these absolute minimum and absolute maximum. Here, these ranges are here to help you with figures like especially the replace. If you are replacing with a value, you don't want this value to be like 2 because it's outside the range that that should be. So these are the absolute maximum and absolute minimum. It's different from the ranges that we provided here because these are used in automatic calibration, which is the next thing that we're going to talk about. So for automatic calibration, you come to this tab. It says perform automatic calibration. It's more or less like the manual calibration tab page, but here you have a calibration algorithm. Now, I had implemented the DDS and the dream algorithm, but for some reason the dream could not stop. If I tried to interrupt it, it kept on going and going. So for now, I fixed it to DDS, but I will, as soon as I fix all the other bugs, I will activate it and you will be able to choose which algorithm you want. Now, it's good that DDS is the one that is working because it's quite efficient algorithm. This is where you select which observation you want to calibrate against. For now, the SWAT plus toolbox does not support multi-site calibration where you calibrate against many observation sites at the same time, but this is something that can always be added in the future. And here you have to choose one. If you want to calibrate against ET, you choose ET. If you want to calibrate against the nutrients, you select nutrients. But as you might imagine, I want to do this for the daily flow hydrology first. And the objective function that you want to use, here we have a few, the NSE, MSE, and the root mean square error. And the idea is to add as many objective functions that you want, kge, log, nse, r squared. These are things that are coming in the future. And for each of the objective functions, you have to make sure that you select the correct direction. Either you want to maximize or minimize. And if you say NSE and then you minimize, you're definitely going in the wrong direction, because an ideal model is the one that is as close to 1 as possible in the NSE value. So you want to make sure that you have selected the correct direction. If you want, let's say root mean square, then you want to minimize this one, or mean square errors. Where is it? Yep, you want to minimize it. But NSE, you want to maximize. So maximize, and the maximum number of iterations is how many runs it will attempt. If the model keeps improving up to the maximum iterations, then it will just stop, because that's one of the stop criteria. Either it stops because the maximum number of iterations has been reached, or the improvement has flatlined. Now, this second stop criteria, I've not implemented it inside the algorithm, so bear with me, it will just go with all the iterations. But the good news is that you can interrupt the calibration at any point without losing your progress. That means at that point, it will still keep the best parameters, as you will see. Now, let me run this with maximum of 100 iterations. Maybe that's a lot. Last time we ran 90. I'm going to run 20. DDS is quite efficient. So I'm going to run just 20 parameters, and yeah, I've selected channel 1 daily flow, and then this is how it looks, and calibrate. So when I run the automatic calibration, it's going to start changing the values automatically here, and then it will keep the best values here, and the values that are going to be generated are within the range of minimum and maximum. So that's why we put here this range. This helps us when we have an idea where the parameter might be. Let's say the curve number must be reduced by about 10%. Then you can say, okay, the minimum is going to be -15, and the maximum is going to be -5. That's the change, assuming percentage change, of course. So going back to the calibration, here I'm ready to run the model, and I'm going to just click calibrate. So now you will see it counting from 1 up to 20. So with everyone, it's going to go 1, 2, 3, all the way up to 20. And we see here that currently the NSE value is 0.3, but it has kept these parameters because that's the best yet. If the next one is better, it will put those values in the current base and then keep changing the values. So here we see there has been no change in performance. Let's wait. Okay, still no improvement. So it keeps changing these values. Now it's changing this parameter, which apparently is not as sensitive. Okay, now we see there has been an improvement in the objective function. But also, with every improvement, it updates the figure so that you can see visually how everything is changing. And if you want more, you can go to the manual tab and you can monitor the indices here. So this is what you have for every of those variables you can monitor, and it keeps changing. Now if I go back, see, yeah, quite improvements from 0.3 and then 0.49, 0.61. Let's wait if there are going to be any more improvements. Now you can check all the other graphs here if you want. This is the monthly ET, but yeah, it's smoothened out. Maybe I should change the code to have those straight lines connecting. That's better, I think. Okay, back to the flows. So now we are at number 10. Okay, seems like it's not improving so much. Like from here to here, there was a very small improvement. 610 to 612. Let's see. There is also a small improvement here. 615 to 625, I should say. Okay. All right, we see a huge improvement there from 624, 0.645 to 0.73. And let's see, it's still improving. 0.79, very good. And we can see all the other indices here. Yeah, the NSE for nitrogen, nitrate nitrogen has reduced, but that's because it's focusing on the daily flows. And we can check the graph here as well. Wherever you are, it's updating throughout the interface. Even those values that it's using here are also updating here. So if you are watching the manual calibration, you're basically watching the automatic calibration. Okay, this is the 18th. It's not many runs. Normally, you are going to need to run so many of these. Maybe I would recommend something around 500 minimum. Now, here we can see it has finished all the 20 runs. I'm sure if we had more, it would have improved further, but we have seen how it has increased all the way up to maximizing the NSE value. Now we are at 0.81, which is quite a good performance. So sometimes when it finishes, it's the parameter values are not good at that point. Like it was testing some parameters and then it ran out of iterations. The values, the current values are different from the current base. That means you're not running the model with the base parameters. Those results that you have in the texting out folder are not the ones with the best parameters. What you should do is come here in the manual calibration and you can, let's say it was 15 here and when it finished calibration it was like 3 here. What you should do is go through each of the parameters. Like here we see the current base is 0.48 and it's 0.418. Okay, it was 18. Okay, and here we see, yeah, this is the best and here it's different. Then I'm just doing this to show you that you need to have the best parameters when you run, if you want to do validation or you want to run to keep the best parameters in the model before you send it to someone. Okay, negative 25.62 and yeah, the rest I didn't change. Okay, so after you change this, you say run with current parameters. Now it will put these parameters in your calibration in your texting out folder and then run it. And then once that happens, you can verify. Once it finishes, you can verify by clicking refresh model performance to make sure that these are indeed the indices. Now you might have noticed a small change because this here what we are seeing is rounded to 3 decimal places, but definitely in the software it has more decimal places. Now by typing manually some of these values, it means we are ignoring those rounded, and then you might see some small changes in here, but not big. Now let's do a model check. Once you have run, you can check your model to see here we have dealt with the graphical, like the graphs, and then we have dealt with the indices, checking the p bias, and to see is everything making sense, is everything okay. But you want also to check for potential errors. You want to have a general overview of the model to check the hydrological mass balance, and also nutrient balance, and so on. This is where you do it in the model check. So this is the button that you have to click, refresh analysis. Refresh analysis. And from the beginning, you will see an overview of the HRUs. This tells you how many HRUs are there with each land use. Now I know there are 96 HRUs with agricultural land, and 8 with pasture, and 1 with forest. And these are the different land uses I have. But also I can do this based on soils. Now be careful with the soils. Sometimes you have a lot of soils, and it might just be mayhem all here, like everything just looking out of control because you have too many soils to show. But for land uses, it's something that you can always show. It's just to give you an idea which soils. This is not very helpful without the user soil, because you don't know what this is. It can be anything. You need to check the properties in the user soil if you want to know what that is, if it's clay, if it's loam. But for land use, at least we already know that it's agriculture, forest, and pasture, because it's fixed inside SWAT Plus. Okay, here we see a model summary. Maybe we can have more information. Suggest to me what you think I should add in the model summary that you would like to see on first glance. But now we have number of HRUs, which is also here. I know. But number of LSUs, because I use the dominant HRU, and the number, the watershed area in square kilometers. Okay, so we go to this chart here. It's telling you the ET, or the aggregation of selected variable, in each of the land uses. In ET, we have for agriculture 108, but for forest we have 1198. So that shows in agriculture you have less ET, of course, than in the forest, which kind of makes sense depending on the kind of forest that is. But in pasture you have lower ET. If you want to check any other variable, you can just select it here. Let's say you want to check individual curve numbers. Which curve number? You select that and then refresh. Of course, it's going to redraw the graph with the selected. Now you have CN here. In agriculture, the CN is 75, and then in forest, you have quite a low curve number, and in pasture, slightly higher than in forest, which kind of makes sense. And yeah, you have many other things that you can check. You can check irrigation. Now we didn't implement any irrigation, so it makes sense that you have everything zero. If we had implemented irrigation in agriculture, then you should see how much irrigation on average every year you have in the agricultural land. But this is averaged in all the HRUs. It's not targeting a specific HRU. So if you have implemented in a single HRU, which is also small, that might be negligible and it wouldn't show up. Unless you have some significant irrigation, then it should show everything. Anything else interesting? That's pretty much it. You can check evaporation from plant. Yeah, from plant you have a lot of evaporation in the forest, and let's say evaporation from soil. I'm curious about this one. Evaporation from soil is very slow. It's very small in forest, which makes sense. The trees are covering all the ground. There is no direct. Um, the trees are covering all the, so there's some sort of a marching effect. Something also interesting here, we have warnings, hydrological warnings. So here we're being told that the surface runoff might be too high in general. Now you wouldn't notice the surface runoff of all of the entire basin, because if you plot the surface runoff, Yeah, it's giving you per HRU, but we want something that is aggregated for the entire basin, and we're going there next. And yeah, I will show you that. And the next is the ratio of surface runoff to water yield appears to be too high. This is one of the checks that we are doing in the background to make sure that the water balance is, it makes sense. Now, the warnings do not mean that there's something wrong with the model. It's just that there might be something wrong with the model. It could be that you know the catchment better. You know that in this catchment, actually you have high surface runoff. Then you can safely ignore such a warning. But if that is not the case, you see this warning, then it's a heads up that you need to do something about this and try and fix it, and so that it's something that makes sense. And it's also another warning here. Now, notice if we were to increase the curve number, let's say, um, this is just one of the things that I can. Wait, what was the range? Parameters, curve number up to 20. Okay, I'm going to put the maximum up to 20. Run it. And then I refresh. Okay, bad performance, I know. It's a bad curve number, and then you have a different chart. Let's go to model check, and I'm going to set this to curve number. Okay, and then refresh. Now, you see an added warning that the curve number for agricultural land might be too high. And of course, the surface runoff is going to be too high with the high curve number. But this is something that will help you in case you have some weird parameters, then you can know if there is a problem. If your area is dominated by high curve numbers, then by all means, you can ignore them, but it's just to alert you of potential problems with your model. Now, I only implemented hydrological warnings in this version, but I am also working on other warnings for sediments, for nutrients, and so on. So watch out for future releases. The cycle is quite fast. Now, next I'm going to show you the hydrological mass balance. Now, of course, it doesn't make sense considering the high curve number, the high surface runoff, everything, almost everything. Well, you have some significant ET, but almost everything is surface runoff. And yeah, this is just an overview of the mass balance, how everything is partitioned. I'm going to do the same for nutrients, where we are going to have phosphorus and nitrogen in this figure, but I have not had time to implement that. I only started, so watch out for new releases, and also for plants, just a summary of the harvest biomass and everything. We're going to have them in here. That concludes about what we have. Oh, by the way, if you want to remove this, you can just do this to clear the figure. That concludes the interaction with the SWAT Plus model in SWAT Plus Toolbox. It's a free software. Everyone can download it and play with it. Right now, it's a test version. So please, if you see any problems, if you experience any bugs, that it would be great if you report them so that we can fix them and get this as stable as possible before version 1. Check out the documentation if you need more information. Of course, we'll be updating you through the documentation page. Now I'm working on it, but yeah, give it a week or two. I'm going to definitely write everything. Okay.